Good evening. This is your usual face, Engineer Michael Chola. I hope the new year is taking shape. We all need to go for the crossover. I know we are warming up for those. Briefly, I've already given my details earlier on. I'm a PMP practitioner, and also I hold an MSc in Bridge Engineering, Bachelor of Science in Civil Engineering, and Diploma in Building and Civil Engineering from recognized institutions. I think in the order: Surrey University, Guildford, UK, Makerere University, and Uganda Polytechnic Kyambogo, which is now the Kyambogo University. I'm also a registered engineer with ERB Uganda, and also a member of UIPE. And also, luckily, I've also been given, I'm a member of PIAC, Bridge Technical Committee 2024 to 2027. So today I decided to at least to begin talking about pre-stressed concrete. Though I have jumped to start straight away with a simple girder, but I think we shall be zigzagging so that we can talk about the basic, the background theory about pre-stressing system, the types, applicability, and the rest. But for now, let me dive straight into the girder design and then share what I also got from somewhere else. I had a training with Kunwa, based in South Korea, and in 2019, and they took us through the simple girder as an introductory capacity building in pre-stressing system. So this is a simple design report for a two-span, that is 18 meters and 20 meter precast post-tension T-Girder footbridge. Of course, now here in Uganda, I have chosen a trading center somewhere where I come from. You can pronounce the name. It's a trading center. Some will call it ANGAGURA, others will call it ANGAGURA. Many will have fun. So in the introduction, I said this report will detail the design of a two-span 18 and 22 meter precast post-tension girder footbridge. It's a simple footbridge, which is 40 meter in total, for a busy trading center in ANGAGURA or ANGAGURA Trading Center. The design follows Eurocode practices and also utilizes MIDAS. You know, I've been trying to learn a lot about MIDAS. I'm not an expert in MIDAS, but trying to learn. So I've done quite a number, extensive learning. MIDAS civil software for modeling, loading, analysis, and design. In the background, basically just pre-stressed concrete girders are structural elements where internal stresses are introduced to counteract tensile stresses for external loads. This technique enhances the performance of concrete in tension, making it suitable for longer span and heavier loads. And it also allows concrete to be in compression, because you have categories. You can allow concrete to be in compression without any tension, or you can allow tension with limited crack, or you can design also crack. So there are normally 3 categories. But for this case, I think it's going to be with no cracks or no tension. That's category 1. Applicability. You can see the bridges, flyover, parking structures, high-rise building, industrial facilities. So many. Like in Uganda, I know we have been more into reinforced concrete. That's why you can see most of our structures are over-congested with columns and then very short span. But if we begin to embrace post-tensioning or pre-tensioning, we are going to have thinner, longer span and robust structure that are easy to construct once we get the equipment and tools for tensioning system. Very important. So that is where we are heading now. Advantage is that it has increased span length. Actually, it has longer span than reinforced concrete without intermediate support. It reduced the material usage. Thinner section reduced material usage, and then it enhanced durability. We reduce cracking and improved resistance. I've told you you can allow concrete, the entire section, to be in compression, and as you are aware, concrete is very good in compression and weak in tension. So once you can introduce, you subject your concrete into the high stresses from cable or tendons, you now allow nominal reinforcement for ultimate limit state condition. So basically, it is very important. Compression state. Pre-stressing keeps the girder in compression, avoiding tensile effects that create cracks. This prevents early deterioration due to the ingress of contaminants through cracks. Disadvantage, of course, it has disadvantages. Higher initial costs, require high string material and specialized equipment, definitely tensioning equipment. Those are jacking systems, very important. They're a bit costly, and also you have to learn. You need to be expert in the area to know what it is. The cables or strands, they are having stresses up to about, it's actually 3 times the strength of reinforced concrete, about 1860, 1720, 1770, and the rest of it. So it is high. Complex construction needs skilled labor and precise execution. Profiling of the tendons, locations, everything need to be precisely done. Otherwise, it can cause problem. Even in maintenance requirement and inspection, you need to really be knowledgeable to understand what happened. The concrete structure may look with having glittering surfaces, but you may find that if the corrosion is happening inside, you never know, and without knowing, in an instant, you see the structure coming down. Construction, inspection, and maintenance. Construction, fabrication, precasts in controlled environments to ensure quality, and then transportation, transported to the site and erected. Normally, when you have a site at location A, normally if the topology is okay, then you just level it, improve the surface of the area ground for quality control and leveling and construction. And then normally once you fabricate and you stack now this thing and they've all hardened to the required strength, then you now use your low bait and other equipment to transport this to the final positioning. So that is why you can see that the transporting systems here, they talk about transportation, fabrication. Normally it has a separate yard, then you transport a few meters or some good distance, and then you have to have some condition in transit, because it should not cause excessive vibration to cause crack, because we normally try to limit cracks. Post-tensioning, tendons are tensioned after concrete has gained sufficient strength, normally maybe 90% or 80% of the specified compressive the strength, and the rest of it you need to really be to follow that. In the inspection, you have pre-construction, you have to inspect materials and fabrication. Then during construction, you also have to monitor tensioning and placement of girders, and then grouting. All those quality control procedures that we do, it has to be done. Especially for most of these post-tension, they have construction stage construction, whereby they stage construction. If there are many spans, like this is 2 span, you find the first span, then the second span, what need to be done. So all that you also have to monitor. Fabrication, you have to monitor. Inspection, you have to monitor. Launching, you have to monitor. Putting those temporary bearings, and then bearing later on, every stage you have to, even temperature, loading, sealing, all that need to be considered. So in the maintenance, you have to routine inspection. This is now going back into your normal inspection. Check for cracks, corrosion, and other signs of wear, using appropriate tools and intervals for inspection as defined. Repairs, address any issue promptly to prevent further deterioration. I told you, post-tensioning system or pre-stressing, they are sensitive to defects and other things, so normally it has to be addressed as early as it is identified. Preventive measure, apply protective coatings and sealant to enhance durability. In the modeling, I think here, modeling, loading, analysis, and design using MIDAS. Definitely, I'm going to take it through quickly. What I did for that simple girder. In the geometry, you define the bridge geometry, including spans, girder dimensions, support conditions. You also specify the materials, and then once you do so, you can see you start with the geometry. In the geometry, you define You define your bridge geometry, you define the spans, you define the dimension. This sometimes you can have all these sketches done before even you do anything. Then by the time you begin loading, it's straightforward. Should be able to handle that. So in the loading, you need to talk about the dead load, that is self-weight of the girder, and superimposed dead load. Normally, like for this girder I'm talking about, you have the wearing surface, that is the superimposed dead load. You have the guard rails on the side, those are superimposed dead load, while the self-weight is the T-girder itself, which is normally taken care of by, which is permanent. You cast it, construct, and remain. So the one that comes additional to that, like the wearing surface, parapets or guardrails, crash barriers, all that becomes now the superimposed dead load. Then live load, pedestrian load as per Eurocode specification, and then environmental loading, wind, temperature variation, and seismic. I did not consider seismic and wind. I only consider temperature variation, minimum element temperature, and also the gradient temperature. In the analysis software, I think the software uses finite element analysis for accurate stress and deformation, and construction staging, simulate the construction. So you can also do the construction staging here. So for this two span, for a continuous, it's not simply supported. You also need to know that you have about 3 stages to define, so that which takes care of time-dependent material, like shrinkage and creep. All that need to be captured. So basically, that is something that you need to take note of. The design, we have flexural design, and then you have shear design, deflection, pre-stress losses, and the rest. So all this, the software takes care of. Once you do all the modeling and then do all the analysis, everything, you are able to see the output of the bending moment, and then also look at the shear, and then you will check then there is the design aspect that you have to do. So there are 2 stages. You do modeling, loading, analysis. You look at, you see all the results. I'm going to take you through. Then once you are done, then you go into the second stage where you do the design. You design all the parameter required, the procedure needed to be done, and you run a design whereby it will give you whether this section has passed or not, whether reinforcement have passed ultimate limit state, serviceability limit state. Remember, in pre-stressing, normally in reinforced we are more concerned about ultimate limit state, but when you are in pre-stressing system or concrete, you have to actually serviceability limit state become key. That is where you don't want to see deformation, and you don't also want to see cracks if you have designed not to take crack. If you have designed for crack limit at a certain extent, you must also observe that that extent is not exceeded. So basically, that is what you need to do. In conclusion, this report outlined the comprehensive design process of a 2-span blah 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 in ANGAGURA by leveraging advanced modeling and analysis tools like MIDAS and adhering to Eurocode. We ensure a robust, durable, and efficient bridge design. Normally, of course, this is repetitive, is generic in nature. When you write your report and you follow all that's required, and the software, you always know what it is. So this is the model, which this is the model which was done. This is the 2-span. This is the 18-meter span, and then this is the 22-meter span. So this one is showing 2-span of pre-cast concrete, post-tensioning or pre-stress concrete T-girder. That is the model you need to have. And then this is the view, side view. You can see this span is shorter and that one is longer. So that is that. And then the next one gives you, once you have done, you need also to enter the tendons. So your tendons, the way you see, it's like, what I did not do for you is to show you the construction staging, because the first stage comes up to where you see this tendon ends, because you're going to see even the moment, because it is continuous. Then the second one now, because you have created where to jack from or to tension from, then you handle the remaining one. This one is assumed to be not fabricated in the yard. It is assumed to be done on site. because normally footbridges and especially the location I've given you is actually across a main road or a main highway. So that is exactly what it is. So it's not going to be like having unprop system. This is a prop system. So this is showing pre-stressed cable or tendon layout profile. Then what follows is now the dead weight. This is the dead load, self-weight load. You can see here the self-weight. This is the dead self-weight load intensity, and then you have no, I need to correct you. The self-weight intensity is not indicated. It's done by the software. This one is the superimposed dead load due to wearing surface, parapets, and the rate is about 10.2. You have to calculate that. And the width of the deck is about 3 meters. So with a reduced parapets for 0.5 or 5.5, you are left with about 2, and then other loading, so you are able to get the load per linear meter. This is the element temperature. For the minimum one, I only indicated minimum, and then the maximum I didn't indicate. This is the image 5 showing temperature gradient, where you indicate the top to be the difference, the temperature bottom and top. 35. I use 35 as maximum and minimum. 15. As you are aware, northern Uganda is very hot during dry season, which goes to about 37. So I use 35 as maximum and 15 as minimum, giving you the difference of 20. This is a section. This section is 3 meters. Then this is 0.2, the thickness of the flange, and then the overall depth is about 1.5, and then you have a 0.8 meter thick. So it's a single T-Girder going across the road, and then you have, these are the proper section properties given. So what I did also, which was interesting, you can also follow what they call influence diagram. So this is at a 2 meters away from the first support. What I did also not do, I did not give you. You can also get all the maximum values of this. Once you know the maximum value, you should also use the other method, influence method, to determine the moment at these locations. So this one is showing you the influence line, force diagram at a 2 meters. Then as you move forward across, this is around 4 meters, you are able to get this profile, and you can see how it is beginning to impact even on the second span. Here it is smaller, but you see it is impacting further into the bigger span. So now as you go towards the mid span of the first span, you can see mid of first span, you see how you see the variation of influence diagram. So these are the variation of influence diagram across. So normally there's also a method where we can calculate moment and shear forces based on influence diagram. Once you have all these values and you know this area, you should be able to calculate. So this is also generated by MIDAS. These are shear forces due to that varying influence. So this is what you can see. These are different influence lines, but depending on the location where you have maximum moment, you also have maximum shear. This one also is showing you the loading. When you load here, this is where you see the maximum. This rate is the maximum influence value at this point. So basically you can be able to demonstrate, and then that's also where you have maximum for that point. It's not exactly in the middle, it's somewhere, because this is not loaded symmetrically. So this is the shear value, and then the loading that bring that. And this is the reaction that you can easily get from your, and this is the deformation contours of self-weight due to self-weight. So that is how the deformation is. This is a deformation due to the pre-stressing. You know, pre-stressing has hogging effect instead. So when you are pulling, when you are tensioning, or when you tension this, it tends to this support is fixed, this support is fixed, and it's fixed, it tends to lift it up. But when you now load, when you load with a superimposed dead load, then that's when it counterbalances this hogging effect, and then you see it well balanced. So that would be that, and this is another deformation due to now superimposed dead load. And then this is the minimum temperature. It tends, what I discovered, minimum temperature tend to contract, while maximum temperature tend to extend the length. So this length reduces to about 36 or 30 something point. If it's 40, it reduces. Right. So always you have to know for you to know the expansivity effect or contraction effect, you must know the parameters of linear expansivity. You need to know the length or the span, and also you need to know the temperature difference for you to be able to calculate and to know, because this movement is what guide us on how to come up with expansion joint. So I discovered that now you see, when it is hot, the length extend. When it is minimum, the length shorten. You can see where this starting point of XY is. It is beyond. And then when you look at here, the XY, it is outside. You see XY, it is out here. So this is minimum temperature effect. It shrinks kind of, while maximum tends to go slightly more. And this is also the temperature. This temperature rise now, the difference, temperature rise due to 20 difference degrees to difference, tends to behave that way. So this is self-weight bending moment. I told you the bending moment, you see it is not symmetrical because this is 22 and that is. So this is now bending moment, and you're going to see the moment due to, and this is the shear force due to self-weight, and you're also going to see this is how the moment due to pre-stressing is. So it is the other way around. That is how the pre-stressing system behaves. So this is now the shear force due to pre-stressing, and this sharp kink is because there is we have a lap from. But if it was if the cable was to have to be connected without any discontinuity where I did the lapping, we wouldn't have this kink. So this also you need to be aware of, so that you can smoothen it when you are doing detailed design. So this is now the axial effect. When you tension on both sides, you can see that the forces tend to be more over the support, but smaller extend on the leg span and bigger extend on this is the red area. This red zone take bigger section here than this side. So that is the effect of pulling or tensioning. This is now your superimposed dead loading, and then down I think we're going to have something to do with shear forces, and then this is the temperature. This is your minimum temperature, and then maximum minimum have no difference, and this is the temperature gradient. This is for maximum. Minimum is hogging while maximum is down, and then this is the shear force due to temperature maximum, similar to the other one. So this is for pedestrian, because this is a crowd loading, and the loading we have used is being in a trading center. This is 5. That is what we use to simulate crowd loading. Of course, I know many guys will ask for dynamic and other things, but I think this is just to demonstrate how we can also use post-tensioning approach to design. So this is the shear force for due to pedestrian, and then I think this is for a load combination. You can see that because this span is a 22, tends to attract more force than this one. This is already together with the post-tensioning system. So that's how the whole thing looks like, and this marks the end. This is the shear force. So this is briefly what you can see, what you can come up with, and you can go an extra mile to come up with a design report, and then put together, and then you have something you can present. So this one is quickly summarizing exactly the narrative that I put together. But now I will take you and also take you through the model itself, and so that you can see what I did, and then you are able to pick from here. I know this is the most interesting area. So okay, let me try if I can oh, it has cut off some of the things, which is going to cause a bit of problem. Let me see if I can try to see what can I do for you here. Okay, fine. So we always normally we start with the property. You have your property, you have for concrete, this is you define this concrete, whereby you have cylinder strength of 40, and then you have the compressive strength of 50. There we are using Eurocode EN04 has been used. So when you define the concrete, and because this is only one member, I'm not going to, you can also have different concrete grades you can specify. So for tendon properties, you also specify tendon properties. Here here basically you use modulus of elasticity, and then you make sure that you also indicate the weight density, that is, and then you make sure you put the name, and then the rest you leave. But also sometimes you can specify actual steel, and then you go to the real detail. Then not forgetting the creep and shrinkage. These are time dependent properties. Creep shrinkage is very important. You need to know. It has to give you all this detail. I always given the time, the value, the start loading, end loading. You see the 10,000 days and the rest. So you remember during when I was explaining about Karuma, the issue of hardening of concrete, 28 days, and then you move. You see 28 days we're already loading, which we are saying that is a bit risky, though it is suitable, especially in our area where we don't have too much volume of traffic. But when you look at it, normally 10,000 days is more. So you can imagine at the time you are loading, end of loading, you start loading and end of loading. So shrinkage also is given here. And then so that is creep and shrinkage. Then you go to the compressive effect. So for compressive effect, you must also define, and this is where you indicate something I need to show you for the time dependent. Please, here is the characteristic compressive cylinder strength. The C4050. This is where you put your 40. You indicate that, and then for normal the notional lane, you can use 1 for the start. Then you can generate, and you can now update that. Very important. And then for the compressive, it is also here the mean compressive strength of concrete. So if you have done mixed design, and you have done tests, and you have done those standard deviations, and you know now that the average or mean strength of your concrete at 28 days, different testing. So you are now able to do that with the delta, with that target strength. So normally this one, I think it's overdone, though normally you may find if you do your cylinders, that FCK plus the delta, you should be able to get your strength to be slightly above 48, no 40 and above. So that is what normally you indicate here. So we don't need to get anything less, and the formula also is given. So that is what normally is done. Then don't forget the use of sections. Here we are dealing with post tensioning. So here is where you define. Make sure you go to post the pre-stressing concrete command. That's where you go, and then you can now identify. This is a T. You have a T. If you want an I section, whatever it is, the box girder, you can define from here, and make sure you have this property right. So you first do your maybe AutoCAD drawing, you do your sketches, have everything right, then you can enter now this. And also always you come here and make sure this is bottom, center bottom. That's why you see everything is in the bottom. I would have also done what they call center top. Center top would move my dimension measurement to start from top here going down. So all that is what you need to be keen and follow. For reinforcement pattern, reinforcement also always important. You define your reinforcement. So you can see this reinforcement is defined. You can do a quick check and you do your reinforcement. Sometimes you can actually, the first thing you can do, you can model, run a design without putting reinforcement. So you see the ultimate limit state failure, the shear failure. You now know that okay, this is now what. Then you can now define this parameters of reinforcement, and then you are able to these two sections are done tapering system. That 3 different design options I did. If I have a T-Girder uniform all across, this is what you have. Then there's also when I do, you can see from here, when you have tapering, what happened where the middle section becomes smaller. Now you are refining, you are resizing for economy. So but for here we have maintained this section as one. So this is the typical section spanning, going across even at the over support and in between span, but you can refine further. And then the definition of reinforcement, they're all here. So each of these reinforcements are defined, and these are the parameters you use. You do the guide here. For the cover, you come here, you do centers, how many bars you have. Here, unfortunately, it's defining in, I think, Imperial, this American definition number 600. So you can do the SI or the millimeter sizes so that you get it well done. So this is how you can define your thing. Now the support system, we also have, don't forget the boundary condition. Boundary condition, you can see we have boundary condition is also defined. And this boundary condition, you put them as per the construction staging. So in the first stage, if you look at the first stage, my first stage is this one. These are the 2 supports. So the other support is not seen. I demonstrate this is the first, and that is where you are able to see the tendons. I wish I could see my tendon, but I don't see it here. I would have demonstrated that. Where is the tendon ending? So it's not, because now I've taken it this way. So we have the construction stage 1. So construction stage 2, I should be able to see all the 3 support system. You get it? So now I'm done, and then you're also able to see all your, this is the first one, this is the first one, because it stops where the first, I showed you that where you have, oh, it disappears, but I need to check. This is where the first one, and then once you do that, then you do the second one. So I can show now all this and that. When I'm done with all has to appear. You get it? So that is how it should be. So once you model now everything, you should be able to also include what you need. Now the construction staging are all here. Stage 1, stage 2, and stage 3, they're all here. You have to be aware that what do I do in stage 1, what do I do in stage 2. So if you look at stages here, it will tell you, let me see, if I go to loading, construction staging, stage 1, in stage 1 I have what they call element. This element is it. So you also need to come to this group and define all these members. Close here, you close here, you come here. This group is where I define, that is a structure group 1, then structure group 2, then all. So normally you need to know now. So you have done 1 and 2, and then the whole thing, because that has to be defined. So if you go get the user manual, you should be able to get, this is a simple guide, but you should be able, then boundary conditions are all defined here, and then the different load group are also defined. All that must be defined. You define your self weight, tendon 1, tendon 2, superimposed dead load, you have temperature, you have temperature gradient, you have construction stage. Construction loading is the construction load that you have to do, but at the end, when you are now going to do service behavior of the bridge, it has to be deactivated. So those are things that we normally do. So now this is now the last one, and now this is your post tensioning. So basically that is what needs to be done. And having done all this, now you have modeled your bridge, you have put all the boundary conditions, you have put the tendons, you have put everything, even the loadings. The different loadings are all here. This is your pre-stressing loading. This plate, this is you see that it is 1395 kilonewton per square meter stresses you do. You can see that you stress on both sides. You stress here and there, then you're stressing here and there. So both ends. You can also stress only one direction. You specify for the software to be aware. Then we have the superimposed dead load. Superimposed dead load need to be applied. This here. This is what I was explaining the other side. You have to apply it. So what do we do? You first come into this loading, and then you can also have a look at the different loading you have. They are defined here. You have self weight, you have pre-stressing, you have superimposed dead load or wearing surface and utilities, temperature loading. Make sure you define, and the type must be temperature, and then the temperature gradient, also the type must be correct. Construction loading are considered as live load. Some you can define as construction loading, and you are able to do that. So all that need to be defined, and then you are able to do that. So then when you come to define like this superimposed dead load, I want you to also be mindful here that if I go to the loads, here, you are going to see that self weight I want to look at element load, and I want to look at date load. No, not really. I just want to view the display. Okay, so basically I think that is the superimposed dead load. Then this one gives you the minimum temperature, and that gives you the maximum temperature. Okay, they are written in Fahrenheit. So this is 100, which is about 35, and then there is other 50, which is defining 15 around there. But the unit will need to be corrected. If you want to correct the unit, it's somewhere. You go to tools, you come to unit preference. It is a meter here. And then here the temperature move to I change. So I made a mistake somewhere that you will get to know. I had put 100. So here, since it's Celsius, I need to correct this to be 35, not 100. So that has to be corrected. But you will, at least you have understood something here. So this, it was Fahrenheit, which was 100, but now it is actually moved to this one. So that has to be corrected if it is centigrade or Celsius. And then you move to temperature-rise the gradient, where you deduct the upper and the lower. Upper is 35, the lower, which is slightly cool, at 15, so the difference is 20. And then construction loading, which is going to be equipment, then people and other things around 1.5, and if you multiply by about 3, give you about 4.5, the width. So basically that is what you know. When it comes to the traffic, this being a footbridge, I define the lane, and I define it, and the lane which I define is the lane defined, the width is 2.4, deducting the 0.5 crash barrier point, and then being a center, put 0, and the wheel spacing I leave it at 2 because but it is defined, is given, the loading which is given is actually the vehicle load is the pedestrian load. It's not it is here. is the pedestrian load, which is 5 with the factor of 0.4. Okay, so basically that is how it is defined. We did not put any loading here. So for the moving load, you also need to know for moving load, you come in here. So it is defined as FOOTBRIDGE. You come to the second command here where you have the FOOTBRIDGE and permit track is able to accept, and then you do that independent, and then you run your stuff, and that is done. So basically this is how you go about the simple T-Girder or whatever girder form you want to do. Now here we can now go and look at the output. So when you look at the output, I go and view the results. We can look at if you want deformation, you can look at. If I want reaction, I can look at, but I want to go straight to moment, self-weight moment. If I'm to look at it, that is what I have. Can give you the line drawing, or you change to solid, and you can put legend to give you the coloring, and the maximum values are all here. You can also as well indicate the values if you want, so you are able to see it. And it is the same here for self-weight. I can also view the shear force value, and then I can also move to pre-stressing system. I think I try to demonstrate. I move to moment, and then when I apply, that is how the effect of tensioning is on your girder. So basically that is what you look at, and then that is the shear force, how it looks like. The same apply to temperature rise. How does it look like? This is the effect, and this is shear. And then if I want to look at the moment, that is how the moment looks like, due to this is the moment due to temperature rise, so the difference between 35 and 15, which is 20 across the section. So basically these are some of the, and then you can come down to the load due to this is now your load envelope due to the pedestrian loading, and then you can also put the value there. If you want clarity, you can also do that. You are able to know this moment. Once you have all these values, you can also go and look at the combination. Now combination is here. Combination, this is concrete. You can do automatic. You come here in the automatic area, and then you specify like a Euro code, and then here make sure you do both factors if you have to indicate. And because snow loading is not in Africa, here we remove normal snow loading. Temperature will leave, all these other ones will leave. Then you can check that the different loading you put here. Those which give you frequent values, you take them this side. The one with characteristic value, leave them. But here is only for the traffic, no, for pedestrians. So that's how you. So you can also look at the make load combination seats. The thing can make for you load combination. You can also look at the spread seating here, the spread seats here. You view everything you want. You should be able to handle this. So this is how you view, and you can also look at the shear force envelope. Normally for clarity we can remove that, and you can get the value from here. So basically this is how you can look at the different action effects on your girder. So having done that, you can now come to design. You go to pre-stressing. Now from pre-stress concrete design, we have the parameters. In the parameter, make sure it is you are considering all the tendon to be designed. It's supposed to be strands. I think I put smooth bars and wire. It is not right. It has to be strands here, and then all this has to be in place. Having done that, you go to the next one, and you make sure you come to pre-stress concrete design material. Your concrete, everything has to be specified here. The reinforcement, the grade of concrete, you specify. Make sure it is done. Then I think these are design position for where the load, where the results will be. The I and J, the J and the rest of it. You can moment resistance, shear resistance. You want, because most of these members have the I and the J, the I and the JN. So you are saying you give me both I and J. So you specify all that. Then serviceability limit state automatically is given the quotient permanent, there is a frequent, and there is characteristics. So when you're dealing with Eurocode, the serviceability limit state has these three categories of quasi, frequent and characteristic. So since this is automatic combination, it automatically takes there. If you do it manually, then you should be able to identify and send this subsidiary limit combination type appropriately. So having done all these short-term exposure tests, then you come and run perform design. When you run perform design, it will design, and this is how this section will look like. So now you come here, you look at you can see now these are the moment. This is moment. This is moment flexure strength. It has now done all this check. This is where the checks are done. You are able to see that, oh, it has passed. If it has not passed, you go back and improve on your reinforcement. You can still refine the reinforcement so that the ratios are not supposed. These ratios are too much. This has to for economized design, you can take to 0.8, 0.9, 0.75 is better because of side controls. You can do this is mean it is over design. You can see the ratios of applied moment to moment resistance. So it is too much. So that one now, these are things you go back and do. Then you check your shear resistance. Some area fail, so you check why, you check, and also you look at the ratios. The ratios are also very, some are very, yeah, but they're actually all low, very, very low. So this should be over support. So over support, normally you have confusion. So you check and also find out and refine. Section shear bars are very important. Section, revision, and shear bars help a lot in managing shear values. So this is the combined shear and torsion. It seems to have a better stuff. Please let's read about our notes and literature from different authors, so that Kong and Evans, Mosley, and many other. Then even the manuals that are applicable, you get to know all this stuff. And then so for cross section, this is now, you see, at construction stage is telling you this tension area, construction stage is failing in tension, not good, not good. So that tells you to go and revise. Other sections have passed. What would be the problem? You check it. Somewhere I saw the temperature effect, the temperature somewhere I saw Fahrenheit and centigrade. So sometimes you may find our loads we have put is not correct. So you go back and review even your boundary condition, you check so that you are not off completely. So then you make sure that the pre-stressing tendon 1 and tendon 2 is not exceeded. Make sure they are all within the tensions in the tendons. So you come down to in service, what happened? I think in service all the stresses have passed, and the whole thing, the checks are all here. These checks help a lot. It will tell you if it has failed. It will also tell you it has failed, so you correct it. And then I think for principle, there's some area here that also have failed in tension. You need to check. And then you come to crack. I think crack width. Some few areas have failed. You need to check why. That is it. So this is now the design aspect. Earlier on, I demonstrated these commands, these nodes, properties, boundaries, load analysis. This is where we view these members. As soon as you are done and it is okay, then you go to PSC design. Okay, results come in here, where you look at reactions. Can get reaction due to that load. It will give you reactions, and you want the values. You can see this is for the live load. You can also get for combination load 3. It can also give you. Then you can also view deformation. They are all here. This as a result now. Not a combination. All this is now the bending moment and everything. Now once you are okay with this, then that's when now we go to the post-tensioning system, and you start the process of design again here, where you go to parameters, the definitions, you go to material definitions, you go to positionings, design and output position, serviceability normally, and then this short term, they are already specified here. You don't need to waste too much time. Exposure class, your exposure class, now we go to your cover coordinate exposure class. You need to know. Then Eurocode has all the things. You have to get appropriate one and put a thing here. I just picked for demonstration purposes. You may find it XD1 or XD2 or XC, depending on the exposure and the quality of soil and water. You are able to get all that. So once you have all that, you come and run your perform, design, So after you have done the perform design, you are able to generate all that, so it has disappeared. But you can actually run, this one will not take long. You just you click your perform design here, so it will definitely run a design, which design now takes you to how now you talk about whether my sections are okay, it has passed A, B, C, D, or do I need to add reinforcement, do I need to adjust my my tendons. And then it's very important, it's more iterative. That's the most interesting design of post-tensioning system or pre-tensioning system. There's a lot of trial and error, but with the software, it makes it slightly faster. Otherwise, if you were to do the manual design like they used to do in the early 80s and the rest, it becomes very, 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 very difficult to conclude a design within a specified period. So because this software, some of them are, like I always say, MIDAS is user friendly. You make changes, it goes, you run design, and everything is done. It's faster and user friendly. User graphical interface is okay, so it doesn't make a lot of difficulties to upcoming engineers and those also who are doing commercial. It's very important. So that is what I think I needed to share with you. Is a simple continuous T-Girder. I have the confidence to introduce this topic because this is exactly what also I was trained at when I went for a 2 weeks design course with the consultant in Seoul. It's just to perfect and understand the principle governing construction staging of post-tensioning system and the rest. So that's why I decided. But next time I will get for you a complete bridge, a small one with post-tensioning, and to go through how we do that. So this is done. That's now where after the design is complete, all this is now active. You can see now here, all this member is what we are checking. So you check your ultimate system, you check your what you can actually generate. Here now I can put on the and I can view this. You can view your shear forces due to that. And by the way, there is one comparison analysis you need to know, that when you post tension a girder, the area of rebars tend to be less than if the section is not post tension. So that is something we discovered. Even when you look at the moments, this the my values here, it will be reduced, not exactly to the extent of reinforced concrete. This is something I will get time. There's a comparison between also T-Girder, non-reinforced and reinforced. I think that one I will get time before end of the week, so that it become our new year challenge. So basically you can look at this and then you're able to view all that. So in a nutshell, this is what I think pre-stressed concrete. You read about it, the theory. It is basically balancing reinforcement and cables or tendons to give you an economically feasible structure or a section or a member. It gives you longer span. It gives you thinner section. You can subject your member to compression throughout, and because concrete is very good in compression, you will not have problem. But it is sensitive to corrosion. Sensitivity of precast or pre-tension or pre-stress system, the sensitivity to corrosion is high. Recently you saw structures collapsing somewhere in the Western world, and they were talking about is it corrosion? Could have been corrosion that caused the collapse. You have to be careful. And then we shall also talk about what makes pre-stressing. You know, tensioning, the jacking force, the jacking system, the anchorage details are very, very important in holding the cables and the tendons in position. So the forces, the tendon losses, the forces are at the ends, which holds these cables in position and keeping the structure in compression throughout, or with minimum crack as designed. So you also need to pay attention to jacking or tensioning of post-tensioning or pre-stressing concrete members. If you don't know how to do that, it's very, very, very risky, and you will get a wrong result, and the structure will not perform very well. So this is a simple T-Girder for you. I will get a box girder, demonstrate, which is good for a bridge, for both vehicle and a walkway, and then we shall talk better at length, and we learn. This is a learning session. This is what I've picked for you. Anything you need, we can discuss further, and then we do more as we learn to understand, because this industry in Africa now, and Uganda in specific, we are now soon, because most of our new bridges now, the Nile Bridge is post-tension, cable state, we have Kampala-Entebbe Expressway, combining all these structures about 4 kilometers, 1 or 1.5, and then the rest adding the Nalokulonga and Busega. So all these are post-tension. Para is post-tension. Then you go to Esima, which is 890, also post-tension. So now even the pattern of inspection, the pattern of understanding maintenance need to be stepped up, because without that knowledge, definitely you can get into problem. It's a very good system, and and it's not very expensive, but just because we still have very few contractors and experts in the country, there's something not right. They keep saying it is very expensive, but I think it is affordable. So basically, this is what I had to share with you guys. Let me end by saying, enjoy your crossover tonight. Happy New Year. We shall begin the new year with some brain teasing, good stuff, learning. Soon I will also try to elaborate on my growth in the industry without going through this calculation. I discovered that I need to talk about myself. How did I end up at this point 22 years ago? Where was I? How did it begin? So I think next time, before we do another thing, I will try to have a chat on that. So with that, I say good evening, and enjoy the rest of the evening.